China's most recent analysis of 3I/Atlas was not presented as a routine observation. It carried the tone of a judgment. Across every translated version, the wording conveyed the same gravity, the kind that makes skepticism feel almost childish. Nothing about the object itself had physically altered, yet the implications around it clearly had. The hesitation in briefings, the guarded expressions of researchers reluctant to speak prematurely, all hinted at something deeper. If this is what confirmation sounds like, the question becomes unavoidable. What have we been resisting all along? And why does it feel as though 3I/Atlas has been patiently ahead of us the entire time? Blackout. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, operating from Chile, detected an object later designated 3I/Atlas. It would soon be verified as an interstellar comet, only the third ever identified passing through our solar system, following 1I/Oumuamua and 2I/Borisov. This distinction matters. Interstellar objects follow paths that are not bound to the Sun. Their orbital eccentricities exceed 1. They pass through once and depart, rather than looping back repeatedly. Their velocity and approach vectors betray an origin beyond our system. Astronomers committed extensive telescope time to studying 3I/Atlas, tracking its brightness, monitoring its coma, and collecting spectral data. The object is fast, with estimates placing its heliocentric speed near 209,000 kilometers per hour. Then came a critical interval. For roughly 36 hours in late September, several major Western observatories were offline at the same time. The Hubble Space Telescope entered scheduled calibration. The James Webb Space Telescope shifted mission priorities. The European Southern Observatory's Very Large Telescope in Chile underwent mirror maintenance. Gemini North and Gemini South experienced planned downtime. Individually, each interruption was routine. Collectively, they produced a gap where most Western optical and infrared coverage vanished. During this window, 3I/Atlas moved into a region of the sky perilously close to the sun's glare, where any delay sharply reduced the precision of activity measurements. For comets, activity means outgassing and dust release, processes that often peak near solar approach. Miss that moment, and the scale and timing of those peaks are lost. At the same time, multiple Chinese observatories remained fully active. High-altitude facilities in Tibet, Qinghai, and Yunnan continued operating because their schedules and day-night cycles did not coincide with Western maintenance periods. Their instruments provided the only uninterrupted record of 3I/Atlas during the gap. The episode exposed a technical truth. Global astronomical coverage is only as strong as its weakest synchronized link. Even with numerous world-class telescopes, simultaneous downtime in one hemisphere can create a blind spot for a fast-moving target. For 3I/Atlas, that single missed window threatened the loss of vital information about outgassing rates, dust-to-gas ratios, and changes in the coma and tail, all essential to determining its origin and makeup. Echo signal. As the observational gap set in, attention shifted to the next phase of monitoring: the comet's coma, tail evolution, and outgassing profile. The coma is the diffuse envelope of gas and dust that forms when a comet's ices sublimate under solar heat, transitioning directly from solid to gas. The tail is the elongated stream pushed away by radiation pressure and the solar wind. From mid-July onward, several instruments captured crucial measurements. Hubble delivered high-resolution images that constrained the nucleus size, suggesting it could be as large as about 5.6 kilometers across, or as small as roughly 300 m, with coma brightness complicating direct estimates. More revealing were findings from the James Webb Space Telescope and the SPHERE-X mission. They detected a coma dominated by carbon dioxide, with water and other volatiles present in far smaller quantities. SPHERE-X showed the CO2 cloud extending hundreds of thousands of kilometers from the nucleus. This is unusual. In comets native to our solar system, water typically dominates as they approach the sun. The elevated CO2 ratio in 3I/Atlas implies a different thermal or compositional history, possibly formation in a colder outer region of its home system or prior thermal processing before ejection. While Western facilities were offline, Chinese observatories continuously logged the comet's position and brightness changes. The echo refers to how the comet responded to solar radiation, increasing luminosity, an expanding coma, and a developing tail, all captured in sequence. These records bridged the missing section of the activity curve. Without them, the peak outgassing phase might have passed undocumented. One key challenge was estimating the nucleus size indirectly. Scientists inferred it by analyzing coma brightness and subtracting modeled dust scattering. Teams combining Hubble and JWST data applied scattered light models and thermal emission fits to determine dust grain size distributions. Grain size alters how light is scattered, subtly reshaping the brightness halo of the coma. These parameters feed directly into estimates of the dust-to-gas mass ratio, a cornerstone for understanding comet structure and origin. The echo signal, then, was not metaphorical. It described how molecular and particulate emissions answered back when energized by sunlight, and how continuous monitoring preserved a complete audiovisual record of that response. The servers under ice. High-altitude observatories function not only as telescopes, but as data production hubs. During the blackout, facilities such as the Ali Observatory in Tibet, the Qinghai Station near Dalinga, and the Yunnan Astronomical Observatory streamed raw data to local high-performance servers before relaying it to central archives in Nanjing and Beijing. Thin air and low humidity at altitude reduce atmospheric interference, boosting signal-to-noise ratios in optical and near-infrared observations. Each telescope followed a similar workflow. Light collected by mirrors between 1 and 2.5 m in diameter was directed on a CCD or CMOS detectors cooled with liquid nitrogen to suppress thermal noise. The detectors output digital counts proportional to photon flux, calibrated with dark frames, bias frames, and flat fields taken before each session. These steps correct electronic noise, pixel response variations, and vignetting. For 3I/Atlas, exposures were kept short, typically 30 to 120 seconds, to avoid image trailing from its rapid apparent motion. Each frame carried GPS-synchronized timestamps accurate to within a millisecond, essential when merging data from multiple sites. Even minor timing discrepancies can distort astrometric results. Captured frames were saved in FITS format, preserving metadata such as telescope coordinates, exposure times, filters, and environmental conditions. Automated pipelines then handled background subtraction, starfield matching, and centroid fitting to extract brightness and positional measurements. Extreme cold posed challenges, with nighttime temperatures dropping below -20 degrees Celsius. Server racks operated inside climate-controlled enclosures with redundant diesel and photovoltaic power. Fiber optic links transmitted data to lower altitude centers for archiving and cross-referencing with international catalogs like the Minor Planet Center. Throughout the September blackout, this infrastructure never stopped. The Ali and Qinghai stations recorded continuous sequences through B, V, and R filters, enabling calculation of color indices that revealed dust composition and grain size. For 3I/Atlas, the indices suggested unusually large, carbon-rich particles. By the time Western systems resumed operations, Chinese servers had amassed hundreds of gigabytes of images and spectra, already organized and ready for global astrometric updates. While half the world's instruments were idle, these mountaintop arrays served as steady heartbeat monitors for an interstellar visitor. Western silence. The lapse in Western coverage was not dramatic but administrative. Modern astronomy relies on scheduling algorithms known as proposal queues, dividing telescope time months in advance among scientific priorities, maintenance, and funding obligations. When maintenance cycles align across facilities, gaps emerge. In late September 2025, that alignment occurred. Hubble underwent gyroscope realignment to maintain pointing accuracy within a tenth of an arcsecond. JWST transitioned between instruments, requiring over 24 hours of thermal stabilization. The Very Large Telescope paused for mirror cleaning using carbon dioxide snow and high-pressure nitrogen jets. Gemini North and South shifted to pre-approved planet search programs. The outcome was a 36-hour span with no major Western optical or near-infrared telescope observing 3I/Atlas. Backup survey systems were also constrained. Pan-STARRS focused on near-Earth asteroids using different filters, while Atlas prioritized potential hazard follow-ups. Radar facilities like Goldstone could not track the comet due to distance, exceeding its roughly 0.1 astronomical unit detection limit for small icy bodies. To the public, such pauses are invisible. Telescope data are not live feeds, but discrete, scheduled integrations. When exposures stop, information simply ceases. For 3I/Atlas, the result was a break in its light curve, the brightness record used to infer rotation and jet activity. Missing segments introduce uncertainty, weakening models of how the comet spins or vents gas. This dependence on overlapping coverage reveals a systemic vulnerability. Most large instruments cluster between 20 degrees north and 30 degrees south, primarily in Chile, Hawaii, and the Canary Islands. Downtime in one hemisphere leaves the other under-equipped. Smaller observatories exist elsewhere, but few match the sensitivity of Hubble, JWST, or VLT. During those silent hours, responsibility shifted entirely east. Chinese logs became the bridge, allowing later Western observations to be re-anchored. By the time systems restarted, 3I/Atlas had traveled more than 1.2 million kilometers. Without the intervening data, its predicted position would have drifted by tens of arcseconds, enough to miss it entirely. The upload. Every astronomical image travels a long digital path before becoming science. Once the plateau observatories, their runs on 3I/Atlas. Exposures were written to FITS files and transmitted via secure fiber to the National Astronomical Data Center in Beijing. The NADC serves as China's central repository, mirroring data from ground networks, space missions, and FAST. Its redundant clusters operate at petabyte scale, using real-time checksum verification to prevent corruption. As the first data packages arrived from Tibet and Shanghai, automated scripts validated metadata, UTC timestamps, telescope IDs, coordinates, and filters. FITS headers followed the IU Standard World Coordinate System, enabling precise alignment across instruments. A secondary pipeline generated low-resolution preview images for rapid inspection. Within 12 hours, the first blackout period images appeared on the China VO Sky Survey portal, a public archive modeled after NASA's MAST. They were routine postings, not press announcements, but for astronomers elsewhere, they were the only available data. Each frame carried measurable detail. The nucleus centroid was determined to within plus or minus 0.2 arcseconds. Differential photometry showed the comet brightened by about 0.3 magnitudes over the gap, signaling a clear rise in activity. The coma appeared slightly elongated sunward, hinting at a transient jet. These measurements were cross-matched with global databases and submitted to the Minor Planet Center. Incorporating them tightened orbital residuals from plus or minus 25 arcseconds to under plus or minus 5, enabling efficient reacquisition once Western telescopes resumed. Bandwidth from the mountain stations was limited, so bulk transfers continued overnight using differential compression. By completion, the dataset spanned hundreds of gigabytes, cataloged by time, filter, and exposure, forming an unbroken photometric sequence across the 36-hour blackout. When JWST and VLT came back online, analysts worldwide were already using the Chinese uploads as the baseline. Without ceremony, the official observational timeline of an interstellar comet had been rewritten. The instruments of trust. Telescope images gain value only after calibration and verification. Calibration ties instrument readings to physical standards, Verification ensures reproducibility. For the 3I/Atlas dataset, compatibility was the first concern. Western facilities rely on unified pipelines like ESO Reflex or AstroDrizzle, while many Chinese observatories use custom systems in Python or IDL. Merging datasets required reconciling wavelength scales, flat field methods, and photometric zero points. Zero points convert digital counts into true magnitudes. Discrepancies can make the same object appear brighter or dimmer across datasets. Chinese teams anchored their measurements using standard Landau photometric sequences, then cross-matched them with Sloan Digital Sky Survey stars to convert into the AB magnitude system. Spectra were calibrated with hollow cathode lamps emitting known lines, keeping wavelength errors under 0.05 nanometers, within international standards. Astrometric alignment followed, fitting comet positions against Gaia DR3 stars to achieve sub-arcsecond precision. Errors here directly affect orbital models. Incorporating the Chinese data reduced the mean residual below 0.2 arcseconds and confirmed 3I/Atlas's hyperbolic path, with eccentricity near 1.19, affirming its interstellar origin. Data integrity demanded independent checks. The National Astronomical Observatories of China invited verification from Hong Kong University of Science and Technology and